go ahead and start. Welcome to Kotlin Under the Covers. I'm Chet Haase. I work for Google. I managed the UI toolkit team inside the Android team for several years. Recently, I switched to the developer relations team so that I could have more time to do things like this. So first of all, let's get a handle on the audience. Who here does Android development? I count 7, all right? Something like that, a small-ish number. And who here uses Kotlin currently? All right, so Kotlin wins over Android, apparently. Maybe a quarter of the audience doing Kotlin. You actually don't need either. This is more of an exploration for some of Kotlin's features. We'll see some Kotlin code, yay, but you don't need to actually understand it. We'll just sort of walk through the pieces and explain as we go. I obviously talk about Kotlin in the context of Android, but today it doesn't really matter. I use Android as a way to get the information about how Kotlin works, but it's sort of an implementation detail of the talk. Again, you don't need to be an Android developer to be here. I'm just talking about language stuff. So, Kotlin, I think people that have used it for a while, is awesome. You could define it like that. It's very concise. There's a lot less boilerplate code, especially these data classes and just all the stuff that you don't have to do that we're all used to doing after years of using the Java programming language. The extension libraries are very powerful. The ability to add extension methods to any class you want is also very powerful. The best thing, especially from an Android point of view, is the compatibility. The fact that we developed all of these APIs using the Java programming language for years, and now we want to introduce a new modern language, and the interop just works. That allowed us to do that. Otherwise, we wouldn't have introduced a new language for the Android platform at all, because it's too painful to then have to develop this parallel set of APIs. So the fact that you can actually just call Java from Kotlin and back and forth means that it's really viable in a Java ecosystem in general, as I'm sure you're all familiar with. Modern language features. Basically, it started with modern language features, and it evolved very, very rapidly, including most recently a huge feature for using coroutines. Not necessarily a new concept, but certainly new in this language space. It's the ability to do much easier asynchronous programming. So it's really awesome. However, it is also magical, and it is not entirely clear how things work. So given that you're running Kotlin on the JVM potentially, well, the JVM is limited in what its capabilities are. So how do all these new language features like coroutines actually work if the Java programming language doesn't offer them, right? We're still dealing with class files at the end of the day. So I want to take a look at two things today. I want to see how some of these magical features actually work, and also how do you figure out stuff like this. If you want to know, if you're looking at a feature wondering, A, gee, how does that work? And B, does it actually cost overhead that I am unwilling to take inside an inner loop? Then we can explore ways that you can get that information. We can see how I did it for this. I'm going to do it in a different order, though. I'm going to talk about the tools that I use to figure this information out, and then we'll see an example of several features. Not all of the features, there's tons of features, but some of the more interesting ones that I've run into. So the tools that we're going to take a look at today are Kotlin Bytecode and Java decompilation, so we can look at the raw bytecode itself. We can also decompile that and take a look at the equivalent Java code that would be produced. And we can also take a look at a memory profiler. Again, I'm going to use Android Studio, but it's just an implementation detail. Shouldn't bog you down too much. All right, so let's take a look at an example, really simple one for primitive types. So if we define a var and we set it equal to 5, we have type inference going on. So the Kotlin type is going to be a capital I int, and it's going to boil down to a primitive type at the Java class file level, right? So you've got the int underneath. So all of that is good. How about this one? We actually say, no, I want it to be an int. And again, it is, and again, primitive type of int. But what if we say, I want this to be a nullable type instead? So I'm setting it equal to a 4, but it's possibly going to be null in the future. Well, it's going to be a nullable int type, and at the Java layer, that's going to be an integer, right? You can't have a primitive type int that is ever set to null, so the possibility that it may happen means that it gets to be auto-boxed into an integer automatically. All right, so let's take a look at how we figure out this kind of stuff with bytecode. All right, I think that was pretty clear. All right, so if we are using, again, many ways to do this, I used Android Studio to get this information. You dive down in the menus and say, I want to see the bytecode for this thing. You click on that menu item, and it puts up a little editing window over there, and then wherever your cursor is in the Kotlin code, you can see the equivalent code in the bytecode highlighted there. So you see these 3 lines over there. So you can also use a command line tool if you prefer. Java P will spit out similar information formatted a little bit differently. So let's take a look at a simple example. So we have this var I0 equals 25, and we can see the bytecode there where it's got some metadata at the top specifying the line numbers, but there's really 2 statements in the bytecode. There's the byte push. It's going to take that value of 25 and push it extended as an integer onto the stack, and then it'll pop it off the stack and store it into an integer variable. Int variable. And here we similarly say, well, I want this to be an int, and it's going to have a value of 78. And again, it does the byte push extended to integer onto the stack, pops it into an int variable. And here we say, I want a nullable variable, and it starts out the same. It pushes a byte extended to an int of 14 onto the stack, but then it invokes a static function, which looks like this. It says, I want the value of this thing, which is going to box it into an integer and return that value. And then instead of storing an int onto a variable, it's going to store a reference to an object, right? So that is where the auto-boxing occurs for this kind of stuff. All right, so what if I don't actually want to read that kind of code? It's not that hard. It's a pretty simple engine. It's not as hard as some assembly I've seen. We can call it bytecode instead. But what if we don't want to do that? It's pretty trivial to then decompile this into the equivalent Java code. So let's take a look at an example here. We have some primitive type setting going on, similar to the code that we were just looking at. We've got the bytecode over there. Looks something like that. We've seen code like this before. We can click on the decompile button, and that will spit out some Java code, and you can see what it actually looks like at the class file level. Right? So there we have integers being auto-boxed because of the nullable types, just like we saw before. All right, there's a third method, which is interesting to use sometime, using a memory profiler to see what's going on. There's seats up front if people standing in back would rather sit down for the next 45 minutes. All right, so memory profiler, again, implementation detail. I used one inside Android Studio. You can use whatever you would like. Memory profilers are very handy for tracking what's going on with the heap over time, what the heap size is. This is especially critical in constrained devices like we have in the mobile space. It's nice to see when the garbage collections happen, and then what happened to the heap. Are there collections that aren't happening as the heap's staying bigger than you want it to? It's also handy for catching leaks, especially in newer versions of the profiler in Android Studio. And it's good for tracking allocations. For anybody that's an old school Android user, we had something called Allocation Tracker, one of my favorite tools, but it kind of ran on its own, separate from every other tool on its own in the Android space. Now we've integrated all these tools together, so the memory profiler does all of these things. It's very handy for figuring out what got allocated when and what the call stack is, and we're going to see an example of that now. So here we have some very simple code. I wrote it myself. We have a nullable type there, and then we have this function, and inside there we have a tight loop. It's going to run 10,001 times through the tight loop, and it's going to take that int value, and it's going to set it into the nullable int value. And that is going to cause, as we saw before, an auto-boxing. So we can take a look at what happens with the memory profiler to get more information on that. So in Android Studio, you would click on this profiler button. That would bring up a list of all the profilers that we have. We have memory and battery and network and CPU. Click on the memory one. That expands the view. And then we see this interesting bump over here where obviously something happened, right? It would be nice to know what's going on there. So we can put the cursor over that area and see basically all of the allocations that occurred in that window of time. And you see those spit out down below. You can see that there's a line there that says integer, and it allocated exactly 9,873 objects, which is weird because my loop said 10,001 times. All right, so why does 10,001 not equal 10,001? All right, so here's the code that I wrote. It goes up to 10,000, should be going 10,001 times through the loop, but nevertheless, it allocated not that same number of objects. So what's going on is we actually have a cache, right? So when you call value of, you're either going to hit in the cache from a negative 128 value to positive 127, because it's pretty common for code to use integers of these small values. So basically, when the VM starts up, then it's going to pre-allocate a bunch of these things, and then it's just going to use those same objects over time so that we don't incur a new auto-boxing or allocation every time one of these small integers comes up, right? So it's going to cache those when the app starts up, and then value of will either return something in the cache, or it will return a new value if it needs to. And that turns out to be exactly 10,001 minus that many values there equals 9,873. So that's why we had that many allocations going on of integers in that little window in time. So I'd like to get more information about that, so I click on that item there, and that shows all of the allocations of those integer objects, and then we click on one of them, and it shows the call stack. And sure enough, my little method is flagged as the thing that actually allocated all those objects because of the auto-boxing going on. All right, let's take a look at some more examples. What about when? So enums, it's kind of a PTSD trigger for people in the Android space. You can use enums. Enums are great. If you're simply using enums, they boil down from the Kotlin level to an enum at the Java level. No big deal, nothing really amazing going on there. But when you use when, something else happens. When you're actually doing a switch, and a similar thing happens down at the Java class file level. This is not news about Kotlin, but it is interesting to see what's going on under the hood. As soon as you try to do a switch on this thing, then it creates a bunch of stuff on your behalf. So here we're doing a switch on those enum values, and then we're just performing some operation. We're calling some random function based on that switch. So what's going on at the bytecode level? Well, it looks like we're getting a handle to an integer array, and then we're getting an ordinal value from that array, and then we're doing a switch based on that ordinal value, and then we're going ahead and calling the function that was the result of that switch statement. So if we take a look at the decompiled code, we can see that there was some code generated on our behalf, this blending KT $when mappings. And the Kotlin compiler basically created this code to say, well, here's an integer array, and then I'm going to stuff it in with the ordinal values for these enums. And then when we actually switch on the enums, we go in here, we grab the array, we get the ordinal value from the array, and then we switch on the ordinal value instead. So what happens if we do a second when? So somewhere else in our code, we're going to switch on the same enums. It turns out that it creates a second array, right? It's the same enum set, but it goes ahead and creates a second array just in case. There's some sort of safety about ordinal values and ordering of enums that's not entirely obvious from the outside. So it's going to create the second array. It's going to stuff the ordinal values in there for the second array. And then finally, what if we do a switch using a different order? And in that case, it's going to create a third array and stuff the ordinal values in. If you look closely, you'll see that it's actually using different ordinal values for the enums because they were in a different order there. So not that big a deal, but interesting that it sort of does all this stuff on your behalf just to sort of distance itself from the ordering of the enums that you happen to use versus the ordinals that need to be used in the code. So that way, I believe the reasoning is if you're calling code that has these enums and something changed in the order in which they were declared, you're still safe because there's a disconnect between the reference of those ordinal values versus the ordering that they were in the enum. All right, let's take a look at lazy properties. So there's a really common pattern in software. I'm sure we've all done this. There's something that's expensive. We don't want to do a whole bunch of allocations or a whole bunch of work every time we start up the application. So maybe this object doesn't need to be created all the time, so we're going to do it lazily, right? So don't do it as startup, just do it eventually when it's actually required. So the manual approach to doing this is, so this is a really stupid example. Bear with me. So let's say that I want an int object, and I want it to be equal to 573, but I don't want to assign that value yet. I'm trying to keep this simple. I hope you never do this in your code. So instead of doing this, the manual approach to lazy would be to say, okay, well, I've got a private variable that's going to be set to null, and then I've got the public property where when it gets queried, it's going to create this object if it needs to, and then return the value. Right, so in the getter, it says if it's currently equal to null, set the value, and then always return the value, whether it was set before or not. All right, pretty straightforward, but that's a lot of boilerplate code. Wouldn't it be nice And then at the Java level, basically, the decompiled Kotlin code looks exactly the same. So the right thing happens. Nothing sort of magical and mysterious going on there for the manual approach. The automatic approach in Kotlin is really cool. There's one line of code to do all of that, even for non-stupid examples, right? You just say auto-lazy int, the variable that I have, by lazy, and then you assign the value. So you give it a little lambda, and as soon as it's requested the first time, it runs the lambda, assigns the value, and you're all good to go. However, on the inside, here's what's going on. First of all, it creates an array of K properties. So Kotlin properties are expanded versions of what property getters and setters are at the Java class file level, right? So it has increased capabilities there. So how do they deal with this thing? Well, they have an object that they call kProperty, which has those enhanced capabilities. So if you're going to use reflection to get information from a Kotlin property, it's going to need a kProperty object, which stores the class name and the type information. And then it can call the proper getters and setters and do the right thing. So at the beginning, at the initialization step for your application, it's going to create this array of K properties, and it's going to create a single K property for that thing that you want for the lazy value, and it's going to stuff it in there, right? So there's two allocations already, the array plus the object, the one single K property that goes in that array. And then it's going to create this lazy object. It's going to say, okay, I've got this lazy property. It's going to return something called capital L lazy. And then when you get the property, it's going to call this method, which is going to call the get value and then the int value inside of that. Now that could use reflection because that's the standard way to get a value from these delegated properties. So it could go through kProperty, make a call through reflection, which is usually not a great thing to do in an inner loop. However, Kotlin compiler is pretty clever and says, okay, well, we know how to deal with this in a faster way, so we're going to create an extension method, an extension function on lazy so that when anybody calls get value, it's actually going to call directly into this code instead of using reflection. And that calls into this code here, which is faster and better than reflection. However, there's still a couple of condition checks as well as a synchronize block in the middle of there. And then the best part is, here's the initialization code to set up all of this stuff, right? So it was a single line of code for me to avoid allocating an int object. And this is what got allocated and created on my behalf. A whole bunch of initialization code plus a couple of allocations. So avoiding allocation of that int object was even dumber than you thought it was to begin with. However, it's not obvious from the outside that all of this is going on. So I've actually seen somebody on the team at one point, like Android has a mindset from the very early days, a lot of which is not valid anymore, of just do not allocate anything ever if you do not have to, right? So the approach this engineer was taking was, well, I need a rect object, which is 4 ints. So wouldn't it be nice if I didn't allocate that until I actually need it? So they used by lazy to avoid allocating the rect. Big mistake because this got generated on their behalf instead. So just go ahead and allocate that rectangle. I'm not saying don't avoid. I'm not saying to avoid lazy. It is really cool. However, I'm saying it's probably useful for things where it's actually expensive allocations and expensive initialization operations that you do want to avoid because they may not need to happen right now. All right, let's take a look at unsigned. We don't have unsigned at the Java class file level or Java bytecode level, but we do at the Kotlin level. So how does that work? It uses inline classes. We have some definitions here. We have a variable that's a 42, an unsigned in, 21 that's an unsigned in, and then we're going to add them together. So the 42 is just represented by an int. Pretty straightforward. We push the byte onto the stack. And then we store an int value. That's pretty good, pretty optimal. The only trick is when we actually add these things together, then we need to invoke a constructor to actually get this object and do the right thing. But here's the weird thing. The constructor takes an integer and then returns an integer. It loads the integer and then it returns it. And that's it. It's complete no-op. It's a mystery to me why this is happening, but still pretty good. We're still basically dealing with integers here. For most of the operations on unsigned, it does what you would want it to. It just uses integer add, integer subtract, integer multiply. The only problem is when we do a division, it actually needs to deal with information in the unsigned bits, so then it does a specialized call there. So it will auto box and then do the right thing for division. Another example here, so we have an unsigned and then we have a regular int, and we can print out both of those. You would think that they would both use print line, but in fact, print line is special cased for unsigned. So in the case of the ints, we just print it out. In the case of the uint, it actually gets boxed first and then calls into an extension function to do the right thing for unsigned values. Right, ranges. One of the weird things I think when people first encounter Kotlin is how many ways there are to do for loops, none of which look like anything I've ever used to do a for loop before. So people sort of struggle and thrash about trying to figure out how to just iterate through some integers. Where is my for I equals 0 to 10? All right, so there are several ways to do this. You've got for I in a range of 0 to 10, or for an index in 0 until 10, so that's exclusive of 10 itself. Or you could repeat something 10 times with a lambda, or you could do a for each. These look basically equivalent to my eyes, and for the most part they are. Right? These are actually pretty much what you want. It's just going to do a little integer iteration here on all three of these, but on the last one, not so much, right? It's going to go ahead and create an iterable on your behalf, and then iterate through that using good old standard Java iteration. Here's another interesting one. So the optimal one at the top here for I in 0 to 10, what if we gave that a step? So what if instead of just incrementing by integers, we said step 2, here's what happens. It goes ahead and creates this range object so that it can get the start value, the end value, and the step value, and then it iterates using those values. I'm not sure why it does this, but the real mystery is if you say step 1, which is exactly equivalent to the code we had before, you still end up in this code. Not a big deal. This is not a lot of overhead, but it's some. It just has sort of a generic way of doing things that is maybe not quite as optimal as what you were expecting. Inline classes, we saw a little bit of this before. That's how unsigned values are implemented. So here we have an inline class for color, which exists basically just to return the color information. So if you create a color with an int value, then we can get the alpha, red, green, and blue channels back from it. If we're doing a print color, then this is how we use the thing. And then, all right, so what does that look like at the bytecode level? So it's, let's see, it creates the color using the constructor implementation, but this is optimal, right? Inline classes are optimized for the most part. They can make a lot of intelligent decisions on your behalf. So it takes an int and it returns an int. So nothing magical and auto boxing going on here. And then print color is also called with an int, right? We're not actually auto-boxing this color object. It makes the right decision in most of these cases. Something weird happens in equality tests, though, where it seems like these two should be equal. But the first one is maybe not. So first one, A equals B, equals B, it auto-boxes both values and then does an R equal call on those objects instead. Whereas in the second case, it only auto-boxes one of those values and then does an equal check on that. Arrays, let's take a look at arrays. Various ways of creating arrays. They sort of seem the same from the outside. So you can call int array of, and that creates a primitive int array. That's fine. You can call array of, and that creates an integer array. So basically, the more information you give it about the types inside by actually telling it, no, I want the int array, the easier it is for the compiler to make the right decision on primitive types or not. And then finally, you can call this. You can pass a lambda in to initialize the values in an int array, and it does the right thing. It creates a primitive array and then stuffs it with values according to your lambda. Extension functions and subclasses, these are maybe not quite obvious. So again, this is code that I personally wrote. I hope you're proud of it. I am. So we have a class called superclass, and then we have a subclass of that called subclass. I have created a couple of extension functions. So there's this getIdentifier function. In the superclass, it will return the string super. In the subclass, it returns the string sub. And then I create an instance of the superclass called superinstance, instance of the subclass called subinstance, and then I create an instance of the subclass, but I cast it to a super. So the question is, what happens when I call getIdentifier on the super instance, it returns, actually, okay. So there's 4 examples here, right? So there's the 3 I defined above, and then we're also doing a runtime cast. So again, creating a subclass and then casting to superclass at runtime. So on the first one, when we call getIdentifier on the super instance, we get, is anybody awake? Shout it out. Super, yay. And when we do it on the subclass, we get? All right, and when we do it on the subclass, cast as the superclass, we get? Good, super, right. So that is the non-obvious one. Wait, I created a subclass, what happened? And the same one with the last one, right? So we have a subclass object, and then we cast it as super, and we wind up in the getIdentifier function for the superclass instead. It's because of how they're implemented. So these extension functions don't actually become methods on the object itself. They become, like we're not doing like code loading and jamming these things into, you know, the string class or anything, right? Instead, we're actually creating these static methods that just live on their own and they get passed an instance. So we have a static method, getIdentifier, which takes a superclass instance, and we have another one that takes a subclass instance. Right? So when we call getIdentifier on the super instance, it's going to come in with something that looks like a super, and it's going to end up in the static method that takes a super. Same thing for the sub. And the surprising one here is, well, it's coming in with something that looks like a super. It may be a sub inside, but it looks like a super, so it's going to end up in the static method that takes a super, and the same one for the last one. Default parameters, this is interesting. This is a really powerful feature in Kotlin. I wish I'd had it in other languages over the years, where you can set some default values and then you don't need to call all of these. Don't need to use all of the parameters. In Android, in the view classes, we tend to have 4 or more constructors, and they're basically supersets of each other. Right? You either call it with, you know, the base information of the context, or you also provide information about the resources and like this expanding set. If we had had this language feature, we wouldn't have needed that. You just need one constructor with default values instead of what we do now, which is, you know, we sort of start at the first one, then pass in null for the other parameters, and on and on. So really nice way for creating terse code and terse APIs as well. So here we have these 2 parameters. We have A and B, and then we return the value of adding those together. So how is it implemented, since we don't have default parameters at the Java class file level? We've got this adder that is the equivalent of what we defined there, and then we get this code that's generated on our behalf that takes the 2 float values that we saw before, and it also takes this int value and an object value. The object is a mystery. It seems like maybe this is there just to sort of tag it and separate it from anything that may have been implemented. We don't want to confuse the compiler or runtime by having similar methods in there, so they just kind of stuff this marker parameter at the end that doesn't seem to be used. The int parameter is interesting, though. It's a bit field. The int parameter is where the compiler will specify which values have or have not been passed in. Right? So if there's let's see, so take a look at that case. If the bit field it has a 1 in it, then it must be that var 0 was not passed in, so we're going to assign the default value to that, and then the opposite for the other value, and then we go ahead and call the internal function. So basically it walks through there, checks the bits in the bit field, and then sends in the appropriate parameters, grabbing from defaults or not, as the case may be. All right, so let's take a look at some examples here. So if we call it with 0 and 0, so if we call it with no parameters, that means we didn't specify anything, and it needs to use both default values. So the bit field will be 3, and it's going to grab both of the default values and then pass it into the internal methods. Here we're passing in a value for A, and so it's going to specify that B wasn't given and get a default value for that. Opposite for specifying B, and then finally, if we actually specify both values, it just goes directly to the adder function because it doesn't need to walk through all that logic. So it's interesting to think about bit fields. If you think not too hard, you think, well, that means that I can only have 32 parameters. Now, I'm not sure anybody should ever have more than 32 parameters in a function call. Hopefully you don't. But nevertheless, why not play with it? So here's an adder function that basically does the same thing with more than 32 parameters. So what happens there? I kind of expected the compiler to blow up or to say, don't do this, this is dumb. But it didn't. It just added in a second bit field, because what's better than 1-bit field? 2-bit fields. All right, coroutines, very interesting new feature in the last year in Kotlin. So how do they work? Turns out state machines. All right, so here we have a suspend function compute. It's going to print out this string, compute suspend, and it's going to delay for a second. All right, and then in our main function, we're going to print out launching coroutine, and then we're going to go launch this thing in global scope, and it's going to call compute twice. And then it's going to print out a string exiting coroutine when it's done with all this. It's going to sleep at the end, dumb thing to do in real code, but basically this just delays for the purposes of the demo to make sure that all of the coroutines can finish before the function itself is done. All right, so if we look at the printouts that we get, sort of obvious. We launch the coroutine, we compute suspend, and then we exit exactly as we wanted. So here's what's actually going on. When you create the coroutine, it creates this lambda on your behalf that is a state machine. So it uses this private variable internally called label, and it switches on the state of label. So label starts out at 0. It's basically an integer increment there. Starts out at 0, and it winds up in this first case. And says, okay, first of all, I'm going to increment label, so the next time I come into the coroutine, I will skip this case and I'll go to the next one. And then it'll go ahead and call compute. And compute is going to suspend, so then it returns. And then eventually it gets called back later, again, enters the lambda. It says, now I'm equal to 1, so I'm going to go into the second case here. Again, increment the label, call compute, and on from there. So it returns, and then it'll come in a third time, and it won't have any work to do besides printing out that last string. All right, so let's see. We can add some information to the bytecode to print out more about what's going on at that level, just to see the details of what the label is set to. And we can see that our original printout now looks like this. So we launch the coroutine, then we enter that lambda, we enter the state machine with a value of 0, then we call compute. Later, we enter the state machine with a value of 1, call compute. Later, enter it with a value of 2, and then we're done. All right, so that's all of the Kotlin features. The real question is, so I talked about a lot of stuff that may seem like, well, a little bit of allocation here and there is not really that big a deal. Lazy, a little bit more if you're using it for really simple stuff. But the real question is, does this matter? So should you care about this stuff? We, on Android, as I said, in the early days of Android, we really did try to avoid all allocations at all costs, especially at the framework level, the platform level, the code that I was helping to write. But even application developers, they needed to understand that the garbage collector really wasn't fast enough to keep up with random allocations all over the place. Memory was very limited, and it was an expensive operation both to allocate as well as collect. Well, fast forward 12 years in Android's life, we have a new runtime that's really amazing at a lot of things, including allocations and collections. So we've been going around and we've been telling people, don't worry about it. Enums are okay. You can do the things that you need to do to have actually elegant codes and APIs that you need. So were we actually lying to you? Do you need to care about all this stuff in Kotlin? No, we weren't lying. Android's doing good. The ART runtime is doing good. Including allocations and collection, which was the real pain point in Android over the years. However, I think it's always good to understand actually what's going on underneath you, right? Knowing what's going on in the engine helps you make the right trade-offs in your code. So if you are in your inner loop, if you're in something that is going to run in this tight loop over and over and over again, wouldn't it be nice to know what's going to happen on your behalf because of language features, right? So if you happen to use a particular language feature instead of some other one and didn't really understand what's going on, and then you run the memory profiler and you say, wow, I just took a huge hit in heap, or I'm suffering in performance time because it's allocating a bunch of stuff, it's kind of nice to actually know how the engine underneath you is working. So do try to understand things. and make the right decisions. In most cases, this really won't matter, but if it's an inner loop, then think about the language features. One quick note, there is apparently a company called Google that has a booth and can tell you interesting information about startup support, all kinds of information about clouds and Google Cloud Platform credits. Also, we are apparently hiring for the Warsaw office. So go to this URL or stop by the booth, and thank you.